When you turn it around, you have the structure which is now used in the Sagrada Familia. It only has compression forces in it, which made it very strong. Similarly, Heinz Isler approached in a similar way. He used nets or cloth to make a hanging model, which he then solidified using a resin or gypsum or something like that. And turning it around, he could construct very thin shells. So he made several projects around Europe, a couple of shown on the left side. But these were all constructed without use of any computers. Around the 1960s, there was a change. Computers came into in the office. First, I want to look at a building that wasn't constructed using computers and tooling like that. So, using the method COS, they calculated a lot of parts of the structure. We at VeriCon, we very much like this building, and we also made it a project to analyze it and go into the archives in Eindhoven to find out how they could make such a thing back then. And very interesting to read on it. That they combined the hand calculations with model testing at TNO. On the right side, you can see that the dome was tested for local buckling. And in this way, they verified that the hand calculations were correct. Because it's a very large span. I think only 10 centimeters thick, the dome. And it spans around 71 meters. So you have better make sure that your calculations are correct then. Then I want to take you to Sydney, to the Opera House. This is credited as one of the first building that was constructed using computer calculations. But they weren't as quick as we now are used to. I once read that it took about a week to prepare the data for the computer model, and then a further week for the computer to actually calculate, to do a calculation run. And after that, they also have 2 weeks to analyze all the numbers that the computer spit out. So it was a very time-consuming process, and that engineering part took also 3 years to do 12 iterations of this building. So, but the first steps were made. New insights were made and evolved further on into the future. And we look at the 90s and the first decade in next millennium. We see an introduction of a lot of software packages. I named here a few, but there are lots more. And this allowed for ever-increasing complexity in buildings. For example, the Petronas Towers, they were back then the highest building that was built. And they used finite element software, but also the use of new materials. So, and again, new tooling for the structural engineer to make make the boundaries a little bit further. In 2008, at the Olympics, the Beijing National Stadium also known as the bird nest, was erected. And again, a next step in the tooling kit for the structural engineer. They used algorithmic design. So using algorithms, the structure is defined, and using FEM software, it is also calculated. And then this decade, again, even more software is available to do the calculations. But when we look from the 90s until now, some interesting trends can be seen. And I will focus on the high-rise buildings. Currently, the Burj Khalifa is the tallest building, 828 meters. It was erected in 2010, so already 10 years now. These are only the highest buildings at the time. And you see, when you look at the data of how many buildings, large buildings are erected, you see an increasing trend. I listed here the buildings over 150 meters. So these are all taller than the buildings available built in the Netherlands. We have a few exceptions, but as you can see now, in a period of 5 years, the last 5 years, approximately 1,300 buildings larger than 150 meters worldwide were erected. We have an increasing part, even extremely tall buildings like 250 meters or even 400 plus meters. And the way this has been possible is by the introduction of all those software toolings. So we can calculate the building more quickly, not like with the Opera House that it took 1 month to do a calculation run. And we couldn't do so many buildings like this. Also, the algorithmic design is still around, so interesting shapes are developed, which now can be calculated using those tools. But it doesn't stop here. When you look at buildings that are planned now, there are currently 211 buildings taller than 500 meters that are being conceptualized. Of course, most the extreme ones, they are very far down the road, like the top two. I have pictures on the right, 4 kilometers and 3 kilometers high. You can see at the drawings that they are not that close to realization. Just some very nice pictures, but it shows how much work has been done over the years. This brings us to the future. But when we look at the timeline, we can learn a couple of things. That we have ever-changing methods and tools. Our toolkit is fuller and fuller. But from the Eiffel until now, the challenges are still the same. We want to further the boundaries, step over them, and increase our knowledge and possibilities. I want to show you how at VeriCon we use these new tools in 2 projects we have recently done. On the left, the Mall of the Netherlands in Leidse Hagen. We have finished this around June this year. Work, and the last parts are being assembled on site, so it's almost finished. And on the right is a production facility of the Veerman Tunnel in Rotbyhaven in Denmark. This was a tender, but we approach this also using the new techniques. So I will also show you that. The first Mall of the Netherlands. Some data. It's located in Leidse Hagen, in the Randstad. And our work consists of engineering the facade structure and the supporting structure. The length of the facade is around 1.5 kilometers, and the area of the facade, the concrete, is around 10,000 square meters. It will be opened next year. It's the largest shopping center in the Netherlands, with basically on one floor with a small section, 2 floors. The scope of work was twofold. The concrete parts, they were glass fiber reinforced concrete elements, 40 millimeters thick, and they are supported with two gradations of 2 layers of steel structure. The tertiary layer is very fine, which is connected to the concrete, and the secondary layer is the connection between the tertiary structure and the main structure. But just a couple of pictures to show some variation, because this facade should resemble a cloth hanging around the building, all the folds in it. To engineer this project, we had to work together with various companies, and this highlights the complexity and the multitude of software you have to use nowadays to address such a project. So first, we decided on a set of rules for the elements and the connections, etc. They are the basis on which the design is made. From this, using these rule sets, MBX made a model in Rhino, and using Grasshopper as well for the concrete parts. And they also modeled the position of the inserts. That was the main communication tool between them and us. Using Rhino, the model in Rhino, the 3DS model, we imported that and we analyzed it. Using Grasshopper, we placed components in our drawing software Tekla, and we calculated from that model also the concrete elements using Karamba. Further calculations were made with other software like SIA, Matrix, IDEA. So there was a multitude of software tools we had to use to engineer this project. But we weren't alone in the world. There was a back structure as well. So we had, using IFC, we communicated with third parties. There were basically no drawings made for this project. All was based on 3D models. And then in interaction and optimization with MBX, we again gave input to them, and they would start producing the concrete elements. And because every element has a different shape, it would be very expensive to make a mold for every specific element. So what they would do was make a big block of wood and mill it down. And the software determined what the optimized order would be. So that you could make the most elements out of one block. And you wouldn't mill too much in one go. Also for the elements that weren't that curvy, they used flexible molds. So they were two types of molds that they used. We also designed and engineered the steel structure. But in order to then we sent the Tekla model to Muskops, who made the secondary structure, and they made from our model. They made the technical drawings for their production environment. The tertiary structure, they were U-shaped or L-shaped basically. We draw them in the final form. But Marten style, they had to unfold that so that you could laser it out of a flat plate. But the only information that we exchanged were step files or AutoCAD files. And they used SolidWorks to unfold it again. And then lastly, TGM, they made assembly drawings for the work on site so that people would know where to put every element. And they used the basis from our IFC model. And we ourselves made reports, the calculations, and some overview drawings for submission to the government authorities. So that were basically the only drawings that were made. This overview shows how complex the data stream currently is, and that all parties have to be able and willing to collaborate very closely, make such a project a success. As the first picture, the rule sets were very important. So here's one. We determined how the spacing and the measurements of a plate would be. And some calculations were made. On the left is using IDEA. This is a model that can extract data from the Tekla model. And like that builds up a calculation model. And on the right, using SIA, there was a hook. I'll show you later where it's used, but this is how we calculated that. Then I want to take you on a small tour through the building, IFC tour, I call it. I hope it's a bit visible. I expect it to be a little bit choppy, but
it's visible.
Okay. This is an overview of a part of the Mall of the Netherlands. This is around half of it. Otherwise, the model would be too big. So I want to take a tour around here, starting at entrance number 7. Like this, entrance number 7, through 6 here, and finishing this part, the main entrance, the most complex part of it. Here are some views. First, let me show you to take you to a simple, basic design. Typically, the concrete parts would be attached to such a structure, L structure, which is hanged using those hooks here on pins in a U-shaped section. The U-shaped section is connected to the secondary structure, which is a big truss, which is connected to the main structures using intermediaries. So that's basically the structure. But this is the basis. Another basic part is for the band on the roof, so that sticks out around 2.5 meters, I think, and it's covered with concrete parts around here. Here's an element, be an element. There would be an element, and on top would be an element. And this is also hanged with one hook, and on the bottom it's compression here, and it's using a bolt to position it correctly. And as you can see, it's a complete model with all the hooks and holes and things included. Even the number, the part number is lasered in. So this is the basic. But, then I'll take you to the entrance part, and you see already some complexities arise. Here it's not connected to a vertical, but a horizontal plate. So we had to engineer L-shaped hockey sticks, as we call them. And because everything is curved, and you had to allow for very large tolerances of around 20 millimeters. So this made it even more complex, because on every connection you have to make sure that those 20 millimeters were allowed for. So I go to entrance number 6. There's a large curved area, curved trusses for the secondary structure, as you can see here. And like entrance number 7, I just show you, there are also those plates, hockey sticks, and very complex engineering. A lot of different solutions we had to provide for, because every situation is different. Just the detail of such a plate. I'm going to the other side, to the main entrance. I also included the concrete part here now. So you can see how those elements are aligned. So all the lines are parametric defined. Remove the concrete, you can see how complex this is. Just highlight a few things using this one, so the back isn't as cluttered. You have those plates again, but as it's curved, every plate has a different form. They are connected or stabilized using a cross like this. And all these parts were placed using scripts from Rhino, and then they were enhanced using Tekla. Just to show you a few things, but looking at the time, I will finish this now. And we look at some real-life pictures. So here is a part at the basic structure. See the U-shaped with pins in it, and there the hooks will connect to. This is a zakker, as we call it. All the parts in the building have names. We have given names. But you can see all the concrete parts are very different, but they align very, very nicely. Like this, they arrive at the building site, reassembled as much as possible. This is entrance 6, as we just saw in the IFC model. This is how the finished entrance looks. This is the main entrance. We show all those hockey sticks, U-shaped hockey sticks, connected uniquely to the main structure. When we visited the building site, all around were piles of full steel elements they have to connect. And we had a small challenge to know from the number where it should be. And probably all engineers knew exactly, because it was a lot of work. They were like little children by the end of the project. So we knew a single one of them, basically. We also have a video on the VeriCon YouTube channel of the project, but considering the time, I would like to ask you to see it there, and we continue to the next project. That's the production facility of the Veerman Tunnel. It's a tender phase, which finished last week, and we didn't win it, but we were second, very closely, as they told us. But the approach this project, it consists of 3 production halls, a combined area of 80,000 square meters. Also, we have parameterization tools. The reason for that was given as we had only 6 weeks for the tender period, so that was very very short. And also, if we got the assignment, then we would have only 3 months to actually engineer it. So you have to use the new tools available to address such a big project. As you just saw, the project consists of 3 holes. A and B are equal, and C is basically half of the hole. And a big hole is 250 by 200 meters with a height of 30 meters. A very large project, but it's only used for constructing the tunnel elements used for the tunnel. So the design life was only 5 years. So it, one of the main goals to make otherwise waste of such amount of materials. This video I want to show you that gives a bit of an overview, a quick overview of the project.
Also, I'd like to remind you that we still have only 5 minutes left.
Okay. No, then I'll just show you a picture. This is how it would look like in a render. For this project, just to finish up, I want to show you how we used Grasshopper for this. This is the script used for one of the elements. This is this girder here. We used a section for parameters, structure generation, calculation and optimization routine, and this bottom part are the load cases considered for this part. With the parameters, we could optimize the building. And here are some key figures: how much steel, kilograms per square meter, were used. I won't go into detail about this, but here is a routine that makes calculation and the optimization. So it looks for changes the cross sections of the parts such that the unity check is as high as possible. And we allowed for 5% redundancy. Small video. There you can see, like I said, here is the kilogram per square meter and the unity check. And we are now changing the height of the truss. And you can see using this slider, you can optimize the dimensions of the truss. Next, we vary in the number of divisions. So more divisions lead to more structural parts, but also to thinner parts. But there's also an optimum. And in this matter, you can very quickly, in a couple of weeks, engineer such a large building. We did not only do this for this part, but the complete roof. We address like this. So that brings me to the end of the presentation. Normally, I would be at the university, and we like to always give a goodie bag. So, but that's now a bit difficult. So, if you still want one, I'll translate it. You can go to this address and leave your details, and we will send you the goodie bag. I want to finish with a quote from the engineer from the Opera House in Sydney, concerning all the new tools that we have. If you don't know the order of magnitude of the answer, don't choose the computer. And that concludes my presentation. If there are is there any time for questions, then it would be now.
Okay, the question was, what's the why is Tekla more favorable over Revit? Revit or other programs?
If I understand correctly, why we chose to use Tekla instead of Revit, for example.
Yes.
When we started the company, we looked at several software packages, especially for the drawing, and we came to the conclusion that Tekla would have the most ability to address those problems, and especially not basically the drawing part that could also be done in Revit, but especially the part where we can produce production data and send that to other companies that produce the actual parts. That's where we feel that Tekla has a step further.
Is there another question? Yeah. You showed the nice models, the integration or the way you work together, but how do you manage? There are so many many links in the web.
Of course, we didn't engineer the whole project in one go. So we divided it in two parts, and that was quite manageable like that. But using IFC, we had a weekly update of the model. So every party would upload their new model. So we always had the latest information to finish our work. And when we were completely finished, we sent our core model, not an IFC or a drawing of something like that, but the basic model, actual model, to the other party to pick it up and do their thing, their part. So it was a challenge, I agree, but it worked because all those curved surfaces and those connections, you have to find a way that everybody knows exactly where a part is, and it's really not possible to make a drawing reflect all that. So this is the way we chose, and every company also had their own preferred software. So we had to look for a way those software packages talk to each other. So you are correct that it was a challenge, but we managed. I hope that answers your question.
Yes, thank you. I don't think there are any more questions. None from our side. I also don't see any questions in the chat. So then I'd like to thank you for giving this lecture, and I thank everyone for their participation. Goodbye.
Thank you.